Okay, so let's look at some of the standard paradoxes, so-called, in special relativity. And what we mean by a paradox here is not something that's not true, but something that seems weird until you realize that you're assuming something from Galilean relativity that's actually not true. Let's start with a barn. And this barn has depth L, and we're going to try and get this rod into the barn. And this rod, rather unfortunately, has a length 2L. And I've got my friends standing here at the door, and they can swing the gates shut or open, so they can let me get this rod inside, but unfortunately my rod's too large. Well, I know exactly what to do to get this rod inside. All I have to do is get it up fast enough until that factor of gamma is in fact a half, and then through length contraction this rod is going to be of length L. And so then this person is going to say it's going to fit beautifully inside. So I'll run it in, run, and as soon as it fits inside, I'll get this person to close the gate. So as soon as the back end of this rod passes through this point, this person will close the gate and I'll have a rod fitting beautifully inside. That sounds strange. Maybe the reason we don't see that is because, of course, it's very hard to get rods up to 3/4 of the speed of light. However, there's another particular strangeness, which is, let's think about it from the rod's point of view. So supposing somebody else is actually carrying this rod, and they have to do all the work of getting it up to speed. But to them, of course, the rod always looks of length 2L. To them, what happens to the barn is that the barn gets shorter, so the barn becomes length half L. So how on earth is this rod ever going to fit? Somehow these two pictures have to be reconciled, and that's a so-called paradox in special relativity. Another classic so-called paradox is the twins paradox. Supposing we have a large blue and green planet with a capacity for international space travel. And on that planet are two twins. And one of those twins gets in a rocket, waves bye-bye to a friend, and flies off at great speed, indeed at velocity v, very close to the speed of light, to a large distance away, and then turns around and comes back again. Right, so obviously, compared to this twin here, who's going to be looking at this twin's moving very fast, which means her time is going to be moving slower due to time dilation. So this twin's clock is going to appear to be going very slow all the way out. And then when she turns around, her clock's going to be going very slow all the way back. So when this twin gets back here, this twin might have aged 100 years and this twin might have only spent 1 year on the actual journey. And so the twins are going to be very different ages. Maybe that's what happens. We've never done that experiment. On the other hand, think of it from this twin's point of view, the one that goes on the journey. She jumps in the rocket, gets up to speed, and then she's just traveling at lovely constant velocity. So when she's looking at her twin's age, her twin appears to be aging very slowly. So there's a whole trip, her twin is aging slowly, and then she turns around and comes back, and her twin's aging slowly the whole time. So when they come back, why doesn't this twin see this twin as being much younger? So there's an obvious symmetry there between the twins, and an obvious asymmetry between what you might expect them to see, and only one actual thing can happen. So what's the resolution of that? So let's work through these two paradoxes. The way you analyze any special relativity problem is you break it down into the key events. So the key events as this pole is going into the barn are firstly when the front of the pole goes and reaches the back of the barn, and secondly where the back of the pole reaches the front of the barn. So let's draw that on a space-time diagram. So we have to pick a frame. Let's start with the barn's frame. And so on that frame of reference, I'll do the world line for the back of the barn, which is going to be constant, at a constant position. And we'll start it at the origin, and we'll do a world line for the front of the barn. So the coordinates of this point, this is the point where the pole is going to be at the back of the barn, this is the point where the pole is going to be at the front of the barn. The coordinates for this point are going to be, and this is the origin. Now our pole is passing through, so it's traveling. So it's going to be the back of the pole and the front of the pole are going to be moving on a slope at the same velocity. And we've carefully designed it so that gamma is exactly 2, so that the length contraction makes this pole exactly of length L at the point, so we can simultaneously have the back of the pole hitting the front of the barn and the front of the pole hitting the back of the barn. Now let's work out what these events correspond to in the pole's frame of reference using the Lorentz transforms. And remember that gamma is 2, so this x dash is just 2L. And indeed, this entire line is just defined as the x dash equals 2L line, just as this line is the x dash equals 0 line. And this line here, the world line of the barn, is the x equals 0, and this is the x equals L. But once again, it's actually the time coordinate that works against our intuition the most. As we can see, in the barn's frame of reference, the back of the pole has gone inside the barn at the same time as the front of the pole is just squished up against the back of the barn. But those two events do not happen at the same time according to the pole. According to the pole, the front of the pole reaches the back of the barn well before, this is a negative number, it reaches the back of the barn well before the back of the pole goes through the front of the barn. So when you're running towards the barn that seems too short, of course, the front of the pole hits the back of the barn first, and the back of your pole hasn't got anywhere near the front of the barn yet. And so in fact, the front of the pole smashes through the back wall of the barn and carries on its merry way up to some point over here, and then it's this point at which we might say that the pole thinks this is happening at the same time as that. So let's calculate what that point should be. So it's got to be t dash equals 0, because that's the time at which the back of the pole is reaching the front of the barn. And again, the x dash has to be 2L, just as this was 2L. So again, we use the inverse version of the Lorentz transforms, where we swap the dashes and the undashed coordinates, and we have a plus instead of a minus for our v's. So we can see that from the pole's point of view, it's a long time after this magical moment where the barn thought that the pole was fitting in it, that the pole finally has the back of it going through the gate. And so the barn sees the pole go beautifully fit just inside the barn before the person with the pole smashes through the back and runs off. And the person with the pole sees this ridiculously small barn, they smash through the back, and then the barn cheers as they close the gate much later on the back of the pole, saying, well, you're fools because it's all gone wrong. So in fact, both of them see the same sequence of events. They see smash and then the gate closing. They just think of them as occurring at different times. The twin paradox is a little bit simpler to explain because we don't have to go through any actual calculations. Where is the asymmetry? The asymmetry is simply in the acceleration. So this twin, the one that jumps in the rocket and flies off, she has to fire her engines. She has to fire engines to get up to speed, and then even more importantly, she travels a long distance and then she has to fire engines to come back. And if you go through the calculation very slowly, it's during the period where she's firing the engines that we get this massive asymmetry between this twin and the other twin. So in other words, this twin, the one staying on Earth, if we ignore the gravity of Earth briefly, is staying in an inertial frame, whereas this twin is not staying in an inertial frame. She's jumping between them dramatically, and that's where the asymmetry comes from. In fact, a gentler version of this very experiment has been done. They had twin atomic clocks. They put one of them in a plane, flew the plane around the Earth, came back, and they showed that the atomic clocks read different numbers. And they've done that, of course, to great sensitivity. And indeed, the speed that satellites go around the Earth, we have a lot of atomic clocks in orbit because our entire GPS system is based on it. All the velocities of those satellites are so large that we have to make non-trivial relativistic corrections to make sure that those satellites work properly.